Okay, we are recording. So now we're in section 12.2, and we're actually going to compute some double integrals. And I'm going to show you how to do this, but you'll see it's not very hard. It's not very hard if you use the concept of iteration. Let me give you a moment to copy this problem down. Okay, so just like when you do differentiation, you do your partial differentiation. You can only differentiate with respect to one variable at a time. It's the same with double integrals. You can only integrate with respect to one variable at a time. So we have this double integral, okay, where our function is x squared times y, and we're going to integrate with respect to y first. The y limits go from 1 to 2, and then secondly, we're going to integrate with respect to x. The x limits go from 0 to 3. So let's see how we do this. Okay, so in our solution, first of all, it's good to know, what does this mean physically? Well, remember, any double integral is the limit of a double Riemann sum, and a double Riemann sum is an approximation of the volume underneath the surface by adding up uh, uh, by adding up blocks, right? Blocks of volume. So this double integral, we interpret this as saying, okay, we are finding the volume between the surface, which is f of xy equals x squared y. That's your integrand here. And the xy plane, so the volume between that surface and the xy plane over the region D. So the region D here, x goes from 0 to 3 because the x limits are from 0 to 3. The outer limits go with the x. The y limits go from 1 to 2. The y limits go from 1 to 2 because the inner integral is with respect to y. So what's helpful? Well, let me let you get caught up to here. Please let me know if you have any questions. Okay, so far are we comfortable up to here? Give me a thumbs up if you're okay with this step here. Okay, wonderful. Angela's good, Narina's good, Mary, Yeva, Matthew. Okay, okay. Well, so now we're going to compute this little integral here. We know the antiderivative of y is y squared over 2. Limits go from 2 to 1. And so we evaluate that. And we're going to end up getting 3/2 x squared. And this is the kind of work I would want to see on your third exam, right? This is on your third exam. And now all that's left is just to compute this little integral. Now, when we recognize, by the way, that this volume, since this function x squared times y is positive over this region D, the volume should be positive. But you know, volume, we can have positive volume and negative volume depending on whether the surface is going above or below the xy plane. All right, we continue on. We continue on here. And we're going to end up getting 27/2. So we conclude then that this volume is 27/2. Now I'll make a comment. You'll notice that all the limits here, all these limits are constant limits. Okay, they're all constant limits. When that is the case, you can switch the limits and get the same answer. So in other words, if you wanted to integrate with respect to x first and then y, okay, if you wanted to do that, you would end up getting 27/2. And this is by a theorem called Fubini's theorem. It only works when all of your limits are constant limits. It will not work otherwise. Okay. So you're going to be doing a lot of integration practice. A lot of integration practice here. Let's do one more problem here. Hopefully we're good. Let me see, Norina. All right, hold on, IB, hold on. Let me get Norina's question first. On the third line. Yes, here. Yeah, it's 3. Oh, do I have an error? There is a little error, isn't there? One moment. It should be, good catch, 3 cubed over 3. Hold on. Thank you, Norina. This is 3 cubed over 3 minus 0 cubed over 3. Excellent, excellent. Please make that change, everybody. Let me check it on my notes here. And then IB, you want to go back to the previous page? Okay, hang on, hang on. All right, so make that change here. All right, going back, IB, to the previous page, okay. Let me know when you're good. Okay, very good, IB. All right, I'll go back to here then. One moment, class. Okay, so I'd like to look at an example from the book then. It relates to, it's example 3. All right, so let me bring that up if we're good here. Okay, so we're looking here at another problem. We're going to evaluate this double integral over region R, where x goes from 1 to 2 and y goes from 0 to pi. And we're going to first integrate with respect to x. Okay, we're going to first integrate with respect to x. Hold on. So the antiderivative of y times the sine of xy with respect to dx is negative cosine of xy. If you, let me show you why that would be. If you take negative cosine of xy and you differentiate that with respect to x, okay, what you're going to get, well, you can bring the negative out front. And of course, you're going to hold the y constant. So by the chain rule, you'll get negative times the derivative of cosine is negative sine. And then the derivative of x times y, if you're holding y constant, you're going to get an x. So that's going to turn out to be x. Now hold on. No, it's going to be y, right? I made an error. Right. So you're going to get, because you're holding the y constant, right? And the derivative of x times y, derivative of x is 1. So okay, so you're going to get y times the sine of xy. So the antiderivative of y times the sine of xy is negative cosine of xy. Hold the phone now. Let me make sure I'm doing this right. Hold on. Yes, the antiderivative of y times the sine of xy is negative cosine of xy. And so if we go back to the problem at hand, if we go back to the book, okay, there is that antiderivative, negative cosine of xy. The angle is xy. You put in x equals 2, you put in x equals 1. And then you got now you got the integral from 0 to pi of negative cosine 2y plus cosine of y dy. Now it's a calculus 1 problem, or a calculus 2 problem, I should say. And you're going to end up getting 0. How can that happen? How can that happen? Well, if you look at the picture here below, there is the surface. There is the surface, and your y limits are from 0 to pi, and your x limits are from 1 to 2, right? X limits are from 1 to 2, and y limits are from 0 to pi. So pi is like 3.14. So on the y-axis, they're showing 0 to 3. So basically that you have positive volume and negative volume, and they cancel each other out. Now, one more thing about this problem. Let's say that you wanted to integrate, because remember, you have constant limits, so you can reverse the order of integration and integrate with respect to y first and then x. But if you were to do that, if you were to do the inner integral, and they show you here, you'd have to use integration by parts. You actually have to use integration by parts to do the inner integral. And I actually worked this out on my own. And in the end, you're going to get an answer 0 in the end. But it was a lot harder to integrate with respect to the variable y first and then x. So one thing you have to keep in mind with these problems in section 12.2 is that sometimes, particularly if they don't give you an order of integration, sometimes integrating with respect to one variable is easier than integrating with respect to the other variable. So just keep that in mind, okay? And you'll be fine. Are there any questions on section 12.2? Who's at least feeling, I mean, it's new, you have to practice it, but how many are at least, this is okay, I'm reasonably comfortable. Okay, Yeva says it's okay. All right. Good. Anybody else? Maybe. Okay. Thank you, Christopher. I always like to end on a good note here, high note. Mary, very good. All right. Wonderful, Norina. Excellent. All right. Let me go ahead and stop the recording here. All right. And this 12.2 assignment will be due next Tuesday. And I will get WebAssign. I will activate those assignments. Okay.